Hello and Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad HAZIQ and my matrix number is 208336. This is the video on lab test for electrical circuit analysis ECC 3115. So the objective of this lab test is to show step-by-step process of understanding the circuit diagram, which is given here, and then construct the circuit, setting the components, monitor the electrical parameters, and show the output in graph form. So the graph form is it will be solving the circuit in which it will show the graph of inductor current when the current is providing the power to the inductor. So to verify the circuit is by comparing the output with the calculation that I have made. So before constructing the circuit in multi-sim, let's uh, let's know let's study the circuit diagram first. So the circuit diagram given is a parallel circuit and it contains a capacitor, inductor, and resistor, which is shown that it is a parallel RLC circuit. So the parallel RLC circuit has two types of circuit, which is the natural response and step response. So which one is it for the diagram? So it is a step response. So how do I know it is a step response? Because initially the power source, the current will be not connected to the capacitor inductor. So initially there are no energy stored in the circuit of capacitor and inductor. So it is when the switch is opened. So when t is 0 or t is more than 0, when the switch is closed, the power source will be connected to the capacitor inductor and provide the power. And then the inductor current will be increasing in the inductor. So before we make the circuit, designing the circuit, uh, let's us look closely to the components that we will be using. So firstly is the DC current source, the switch, the capacitor, and the inductor, and also the resistor. So the resistor is a variable uh, because it will be determine the type of the step response for this RLC circuit. So not to leaving, so not to forget the values that were given here, so that the data output is not different. So this is the variable of R that will be changed, which is 625 ohm, 500 ohm, and 400 ohm. So let's do the design for the circuit diagram. So first of all, let's get the DC current source. Then get the ground that we'll be using later. And also go to basic, we have switch, resistor, capacitor, and inductor. So switch I will be using SPDT. And then capacitor, following the arrangement in the circuit diagram. And then the resistor. So let's connect the components. Flip vertically. And also not to forget to change the value. So this is 24 milliampere, 25 nanofarad, and also 25 millihenry. So the first resistor variable is 6 to 5. Let's connect the circuit. Sorry. So this is the circuit. So looking at the switch right now, it is actually is opened because it will be not providing the current to the capacitor and inductor. So to uh, provide it, we need to close the circuit, the switch. So we need to find the inductor current when the switch is closed. So let's use the oscilloscope and also mention in the lab test that we need to use the current clamp. Take it closer, and then we need to use the ground. So let's look at the graph that we will be obtaining. So let's set it to the scale of time microsecond, because the current will be providing to the inductor very fast. So this is opened, then I will be controlling the switch by using space, and then I will be running and closing the circuit, and let's watch the graph. So let's see the graph. So this is the graph for variable R 6 to 5 ohm, in which this shows that this is an underdamped response because the value is exceeding the value of 25 milliampere. So it is underdamped because it's exceeding and then come back down. So first of all, how we know that is an underdamped response? Because in the calculation I have made that the value of alpha is lesser than omega naught. The alpha is the damper frequency and the omega naught is the resonance frequency. So that's how we determine what type of response it is. And then there will be a critically damped response for resistance is 500 ohms, and then it is overdamped step response when alpha is more than omega naught. For resistor is 400 ohm. So let's see the graph of the other two step response, the other two type of step response. So let's just copy it, duplicate, and change the value of R. So 500 for critically damped and 400 for overdamped response. So let's see these three circuits, these three graphs. So right now it is closed. Let's check it back just in case. Close, close, open. So let's find the graph. This is the graph for underdamped. This is the graph for critically damped. This is the graph for overdamped. There you go. We have three different graphs of step responses. So to see to compare these three step responses, I will be using a different oscilloscope, which will be the 4-channel oscilloscope, where I can connect different inductor current to the oscilloscope. This is the ground. Then I can change the color too. So blue for underdamped, green is for critically damped. So let's look. So let's change the scale of time, which is very fast. Then we need to set each one of them. So let's find the graph. This one. So this is the graph for inductor current when t equals to 0. This is underdamped, critically damped, and overdamped. So to verify these graphs, I have made a calculation, and the function of the inductor current when time is 0 or time is more than 0 is this function in milliamps. This is for critically damped in milliamps too, and then for overdamped in milliamps too. So to verify the graphs, we need to compare the graph with the calculation graph, which is here. So this is the function that I have shown you just now. Let's change the color according to the. So this is underdamped, critically damped, and overdamped, and this is the graphs. This is changed because we need to exclude the unit prefix of milliampere. And then this is a graph it it looks a little bit weird, not the same, because uh, the this graph in Desmos is not stretched, and this is the value of inductor current, which is it should be just like the critically damped, the normal response, in which it will reach the maximum of 0.024 ampere, which is the milliampere of the current source initially, and then this is the overdamped, which is slower over time, and this is underdamped, which is very fast, and also it is exceeding the maximum value of 24 milliampere, and then it comes back to 24 milliampere, but it was the fastest one. So I think that's all. This is the graph comparing this the calculation, and this is the simulation. So I think that's all for the lab test, uh, given that I have shown the processes. Thank you. See you next time.